So let's look at remarks of this equation. So first one is periodicity, whether this one is periodic or not periodic. The solution, if you plot it, it will be have the shape which will be like this. So where it will decay exponentially, and upon reaching some limit it will maintain its amplitude. So upon giving some initial condition and forcing, it will vibrate like this. So this one is not a periodic wave because this point is not repeated anywhere in the system, not even this point. So the first point is it is not a periodic. Second point will be as t goes to infinity, x of t is periodic. The third point will be this solution have two parts. So the one is transient part, so where the solution is decay, and it usually the time period is very small, t is less than infinity. So this one is not periodic and it depends upon initial conditions. And second part will be steady state. So this one is when time is large, when time is approaching to infinity, so this one becomes periodic. So this is depends upon forcing, so it doesn't depends upon initial condition. So the next part will be based on the damping. When the damping is 0, the solution becomes like this. So here this e power minus neta omega t becomes 0. Therefore exponential of 0 becomes 1. So therefore those equations becomes r naught cos of omega t minus theta. So this is omega, it's so then xst divided by 1 minus r square and cos of lambda t minus theta. So here this is one amplitude, so there is a1, this is r naught. So let this r naught cos of omega t minus theta, so let this be r1 cos of lambda t minus theta, unless the ratio of lambda by omega is integer, then this x of t is periodic. Otherwise the otherwise it is not periodic. So for example, so if we have sine t, that means frequency of this term is 1, and I'm adding this signal with different frequency. So this one is, if we individually take, this one is periodic signal of period 1, this one is periodic of period root 2. If we add these two things, okay, if we add these two things, then the result will be not periodic. So then if you consider x of 1t plus x sine of 2t, this one is periodic of period 3t. period 3. So I'm not sure, so we will check this. It is periodic, so the what will be the period, I'm not sure, so you do it as a exercise. Then this steady state solution. So if we say we are interested only in steady state, then t goes to infinity, this x of t becomes xxt cos of lambda t minus theta divided by 1 minus r square whole square plus 2 neta r whole square root of. So this can be written as x cos of lambda t minus theta. So here it is periodic. So next we need to see dynamic modification factor. So what is dynamic modification factor? Is static dynamic amplification divided by static dynamic deflection divided by static deflection, which is x by x st. So this will be given as this denominator term 1 minus r square whole square plus 2 neta r whole square. So this d is the function of neta and r. So r is the frequency ratio, neta is the damping. Neta is the damping, C by C critical. So now if we plot this d and this is d and this is d modulus of d and this is r, so frequency ratio. So let's consider this as the value 1. So how this system behaves if you start the frequency from 0 and you are keep on increasing. So at some point this is the response amplitude of the system. So this will go like this when this neta equal to 0. So when damping is 0, this will respond like this. So when you increase the damping, so how it will behave? It will behave like this. So if you further increase the damping, this is neta 1. You further increase the damping, so this peak will shift to the left, and this is how it goes. This is neta 2, and I'm increasing the damping further. So this is very bad graph. So bad. So this is how it goes. This is neta 3. So neta 3 is higher than neta 2, then neta 1. So this is 0. So this is the how it looks like. So when it close to 0, so this point is 1. So lambda and omega, when these two frequency is same, so at this point, near this point, we will have very high damping. So this point will move leftward towards this point. This is the configuration of R where you get maximum amplitude. So when you increase the damping, this R also will be decreases. It goes when you increase damping, R moves leftwards so that it matches the maximum point of maximum deflection. To calculate where this maximum deflection happens, so we will write this formula: d of R equal to 1 by 1 minus R square whole square plus 2 neta R whole square root. So then where the neta is not equal to 0, so what we do, we need to find the maximum point, so that we are taking the derivative with respect to R and we are equating to 0. So now we write this is 0, so therefore this one becomes in denominator, this is UV rule, so denominator it becomes like this. So d by dx of u by v equal to v u dash minus u v dash divided by v square, right? Let's find where this dynamic modification factor will get maximum. So here we take the derivative of t, so it follows this formula: v u dash minus u v dash. So v u dash becomes 0, therefore it becomes minus u is 1 v prime. So v prime will be, so what is v? V is 1 minus R square whole square plus 2 neta R whole square. This will be 1 by 2 will be this is 1 by 2 will be there. If you take derivative, this 1 by 2 comes here and it becomes minus 1 by 2. So into derivative of the term interior to this system. So interior will be, so we will expand it and take derivative. So if we expand d by dr into 1 minus 2r square plus r power 4 plus 4 neta square r square. So this is the one. So now we write 1 by 2 1 minus r square whole square plus 2 neta r whole square power minus 1 by 2. So derivative is 4r plus 3r cube plus 4 neta square r, so 8. So this is the 1 divided by denominator 1 minus r square whole square plus 2 neta r whole square equal to 0. So then we will write 1 by 2 of, so if we take this 1 by 2 inside, this becomes 4r becomes 2r minus 3 by 2 r cube plus 4 minus 4 neta square r. So divided by, we have denominator 1 minus r square whole square plus 2 neta r whole square. This becomes 2 minus 1 by 2 equal to 0, therefore numerator only becomes 0. So r equal to 2 minus 4 neta square minus 3 by 2 r cube equal to 0. So is this correct? Let's check once. Let's check, is this correct? 2 of 1 minus r square we take derivative 4 r cube, so sorry, this is 4 r cube and 2 8, so therefore 4 r cube, so this becomes 2, so this becomes 2 r cube. So we need to find the root, so root is r cube and dividing it by 2 minus r by 2, 2 minus 4 neta square equal to 0 minus r 1 minus 2 neta square equal to 0. So we take r common, so r square minus 1 minus 2 neta square equal to 0. So therefore r equal to 0 was one equation, r equal to root of 1 minus 2 neta square is another equation. So this one gives the valid meaning. So when r equal to 1 minus 2 neta square, so then we substitute into d of r into neta equation. So what is d of r minus neta is 1 by 1 minus r square whole square plus 2 neta r whole square root. So if we substitute here, we will get 1 minus 2 neta 1 minus neta square. So this is d max. So next we will see this condition, r at r equal to root of 1 minus 2 neta square, we will get d maximum. This condition, this is called resonance. So this is point number 6. Resonance happens when r equal to root of 1 minus 2 neta square and the maximum amplitude of d max will be 1 minus 2 neta 1 minus neta square. So usually neta will be very small, 0.02 around. So you can simplify this equation. So r equal to 1, so d max will be 1 by 2 neta. So why this d is called dynamic modification factor? Dynamic modification factor. Why? So let's assume you have a system and system damping is 5%, so that means neta equal to 0.05 and dynamic modification factor d max is 1 by 2 neta, where neta is very small. So this gives 1 divided by 2 into 0.05, this gives how much? This gives 10. So 10 is the dynamic modification factor. So what it tells is, it says the deflection at resonance is 10 times of the static deflection. So that's what it says. Now let's look at the equation and how it behaves at different regimes. So d is equal to 1 minus xst into d, which means so xst 1 minus r square whole square plus 2 neta r whole square root of. So we need to see how it will behave in different regimes, where regimes means r is less than 1 and another one is r is equal to 1 and r is greater than 1. So let's look at the first one. So when r is very small, this xst is p by k, then x of t equal to in this form at very steady state. So x is very small, this becomes 1, and r is also very small, so that goes to 1. So this goes to p by k, so which is called stiffness controlled regime. Stiffness controlled regime. Let's look at this one, x of t. So x of t equal to p by k, r equal to 1, so therefore first term becomes 0. So this is 2 neta whole square root, so p by k into 2 neta, so p divided by k into 2 neta equal to c by c critical. C critical can be written as 2 m omega, so this 2 get cancelled, p by k omega becomes omega square, so omega will get cancelled, p by c omega. So this one, since it depends more about damping value, so this is called damping controlled regime. Then the third case, so x of t becomes p by k, where r is so large, so therefore r will dominate, r4 here, 2 neta r square, so therefore this will be more dominant, so therefore this becomes p by k into r4, this will give p by k r square, p by k will be lambda square will be omega square, so omega square equal to k by m, so pk by m lambda square becomes p by m lambda square. So lambda is the driving frequency, m is the mass, so since it depends upon only of the mass parameter, this is controlled mass controlled regime. Or inertial controlled regime. So now we draw the diagram and represent this pictorially. So this is 1, so it will goes this, so let's be, there is a little hump, so this one, so first area is stiffness controlled regime, so this one is damping controlled regime, this one is mass controlled regime, this is x, this is d, not x, this is lambda by omega. So now we have seen throughout when there is a change in frequency, how this response of the system is changing. So now we will see how the theta is changing. So we are interested in to know the theta. So this is lambda by omega, this is theta. How this theta is changing, where r equal to 0, r equal to 1, r equal to greater than 1. So let's find it. Theta equal to tan inverse of 2 neta r divided by 1 minus r square. So when r equal to 0, theta becomes tan inverse of, so when r is equal to 0, so theta becomes 0. When theta equal to 0, therefore theta will be 0. When r equal to 1, theta equal to tan inverse of 2 neta by 0, it's infinity, so this is 0, therefore it will be 0 by 0, it becomes indeterminate, so we will take derivative, so 2 neta r minus 2r, so then we substitute the value 0, so limit r goes to 0, so therefore theta becomes tan inverse of 2 neta by 0, so need 2 neta by 1. When this r equal to 1, we will get, sorry, we will do it again, so I made mistake, I'm jumping too fast, so I am applying 2 neta 1 minus 1, so this becomes infinity. When tan inverse becomes infinity, theta equal to 90 degree, so pi, so now yes, so when theta is goes to very large number, so therefore theta equal to tan inverse of 2 neta r, and 1 minus r squared will be r square, so therefore it becomes 2 neta by r, so if we substitute infinity here, tan inverse becomes 0, so when tan inverse becomes 0, so it is pi, right. So now we apply this inside here, so when r equal to 0, this one, so this is, so now when at r equal to when neta is very small, so what happens, this is how this one look like, so this is the response, so where this one is pi and center will be pi by 2, this is 0 phase, so when we increase the damping further, so we will get a response like this, so first one, this one is neta 2, so when you increase the damping further, so you will get more transient space, this will be, which one is greater, this one is greater, neta 3, so this is how it looks like. So at the center, at r equal to 1, everything is r equal to 1, every irrespective of any damping, it is pi by 2. When we are going further in terms of frequency, it becomes 5. So when there is no damping, like a green color, so when there is no damping, so like this, so this is the path it follows. So when there is no damping at the natural frequency, so near r equal to 1, the phase shift will be shifted 180 degree instantly, and so these are the some remarks that is very important. So one is how the x is depend upon the frequency, and how theta is depends upon the frequency. So with this we conclude forced damped vibration.